So, thinking about my damped oscillation, I know, and indeed this can be derived from a differential equation, which I would encourage you to do, I think, to show personal engagement and also to potentially get 6 marks on exploration. But I know that I'm going to trace out a sinusoid damped by some envelope function such that my amplitude is constantly decreasing with time, or at least my maximum amplitude is constantly decreasing with time. And you state in your work so far that you're assuming that this time period is constant, so you're assuming it's isochronous. It's not a bad assumption to make. I need to make one more assumption. I need to make the assumption that the rate of change of amplitude, that is how much your amplitude changes with time, is going to be directly proportional to your initial amplitude at that time. That is, that when I'm moving from here to here, I'm losing a lot more amplitude per second than when I move from here to here. So all I'm really saying is that if I'm swinging a greater swing, I'm colliding with more air particles or more fluid particles, losing more energy, and therefore the higher the amplitude at the time, the greater the loss of amplitude subsequently. And I'm just going to have to add a negative sign here, because my dA dt, my rate of change of A, is a decrease. So this shows a decrease, this shows the more I'm swinging, the more energy I'm losing. And so working from here then I can say that dA dt is equal to some constant, let's call it gamma, multiplied by A. And I'm going to integrate both sides here with respect to time. Now I can't actually do that at the moment because I have my amplitude over here, which is a function of dA. That is, they both depend on the same thing. So I'm going to divide both sides by A. So 1 over A dA dt is equal to minus gamma. And I'm going to integrate both sides with respect to time. So I have the integral of 1 over A dA dt times dt, it's just dA, is equal to, and then minus gamma. Gamma is just a constant of proportionality, so I can take that out of my integral. So I get left with minus gamma times the integral of dt. I integrate 1 over A with respect to A to get natural log A, which is equal to minus gamma times the integral of 1 dt, which is just t, and then plus c. And I know that when time t is equal to 0, my amplitude is equal to some initial value, A0, and therefore ln A, naught in this case, because A is equal to A0, is equal to minus gamma times 0 plus c. So I have ln A is equal to minus gamma t plus ln A0. I'm going to combine my natural logarithms. I get ln A subtract ln A0, which is ln A over A0, is equal to minus gamma t. So A over A0 is equal to e to the minus gamma t, and so A is equal to A0 times e to the minus gamma t. Now it's actually this form here that is probably most useful to you, because this means if I plot a graph of ln A over A0 on my y-axis against time on my x-axis, I'm going to get a straight line through the origin with a negative gradient. And that gradient will be equal to minus gamma. And so if you multiply your gradient by minus 1, you find out your damping constant, gamma. I hope that was somewhat helpful, but feel free to ask any more questions that you need to.